Okay, so last time we were talking about the energy balance. So for non-isothermal reactors, so that's the case where we are allowing the fact that the reaction is going to change the temperature to affect the overall performance of that reactor. And so we had developed the overall energy balance, which you can see up here in equation 30. So we had that energy could be added in the form of temperature difference. So that's the Q term. Then we might have shaft work here. And then, of course, we've also got pressure volumetric flow work, which is behind the fact that we used enthalpies that appear in these terms. So these terms show us the energy change due to temperature difference, a temperature change between the inlet and the exit here, so T in and T out. And this was the energy difference due to the reaction itself. So due to reaction, we have this heat of reaction times this conversion of component A. And of course, these two terms came just from accounting for the difference in enthalpy between the inlet and the exit. So it's not the case that this balance appeared by saying that in minus out and then plus the heat of reaction contribution. These two terms are, in fact, the difference in enthalpy between the inlet and the exit. Right? Any questions or comments there? Right, so that's the basic relationship that we have between temperature and conversion. And this doesn't quite show us our reactor design. Remember, the reactor design helps us relate the volume of the reactor to the conversion achieved. It helps us work out the space time and all of that. Whereas this is just the relationship between the temperature change and the conversion achieved. So this is the kind of accounting that looks at the fact that we've got some conversion of chemical species. So you've got some starting reactant set, and then that's converted to some product set. And in the process of that happening, there is generally heat given off. So because the molecular arrangements are different, then the entropy will change and the configuration of the atoms will change. So that's going to give off or take in a certain amount of energy. So that's going to result in some thermal change. And that's just what this relationship tries to establish. So that's what the energy balance is for. In its own right, it's not really helping us with the actual reactor design. So we anticipate we will also need those mass balances and design equations in addition to this. Right? So maybe another thing to note while we're here is that we haven't used anything about the type of mixing or the kinetics here. So we haven't used a rate expression, and in fact, you can't see a rate of reaction in this. So we should read this equation as that if we have an inlet temperature T in and this exit temperature T out, and if all these other factors are as they are, so if we are adding a certain amount of heat and a certain amount of shaft work, and this is the molar flow in and so on, then in order for us to have this specific temperature change, then we must have converted to this extent. Right, so that's the way to look at this equation. Right, for us to achieve this conversion, we must have that temperature change. So that's what the energy balance is giving us. Right? Any questions on that? So let's use that now in our reactor designs. We had also discussed this last time. We said that if we have heat being added, right, if we expanded on Q dot and we said that because this is the heat being added due to temperature difference, Q dot generally can have that form. And then because the temperature difference, this might apply locally, so this might be at some specific point, there's a specific temperature difference. But if we try to get the overall temperature difference, if we try to average that out, then we saw that we could use the log mean temperature difference in the case of a double pipe heat exchanger. And we applied some approximations here. So we applied the approximation that if the flow rate was high enough, then that simplifies to this form, right? So It can be as simple as this, but this is under the assumption that the flow rate is quite high, which means that on the jacket side, on the heat transfer medium side, the temperature difference is approximately zero. So that's the relationship that we had established there. So this is saying that if we achieve a certain temperature in the reactor T, so this T without a subscript, that's the reactor temperature. Given that we entered at T in, and given this temperature on the heating medium as TA, and then given all these other constants, that for this to happen, for us to accomplish this temperature T, given it entered at T in, then the conversion must have been X here. So the conversion must have been this arrangement of all of those vectors. Right. So it's the same thing as we said before, just a bit more in the context of having a heat exchanger there as well. So here's this example where we are looking at the same components that we had discussed before. So we had A plus B plus gives us C plus D, and then we also had an inert, and then we had outlined the heat capacities and the heat of reaction and so on. So now we are extending that same example, and we are providing here the overall heat transfer coefficient and then the heat transfer area. So it's just 1 square meter here, and we are given the molar flow rates and the temperatures and so on. And then also the additional information that we do need is the heat capacity of the jacket fluid. So that's the new thing. We've got a heat exchanger, and then that's pumping through some heat exchange fluid, and that has its own heat capacity. That's a different component now. So that's provided, the heat capacity is known, and then we want to show how the conversion varies in that range. So from a temperature of 300 to 350. So that is actually the exit, or I should say the reactor temperature, right? That's not entering at 300 and leaving at 350. That's saying the entry temperature, in fact, is fixed at 340. So this is just saying if we were to leave at 300, so if we were to leave with temperatures in those ranges, then what must the conversion have been? Right, so that's shown here. So you can see that as we are considering these different temperatures, so we are looking at exit temperatures in the range 300 to 350. You can see the conversion is dropping here. And that's also because this is an exothermic reaction. So for us to be operating at those higher temperatures, we get that inhibition effect, and so the temperature goes down. And you'll see there are 3 lines here, and that's because I was also testing that assumption. So you see here, in this question, there is enough information, right? We are told that the jacket heat capacity is that, and we are told what the temperature of the jacket is. So it says here the jacket temperature is 550 Kelvin. So it is possible for us to calculate the log mean temperature difference and use the version of that equation without the simplification applied. So that's, I believe that's this curve, and so that red curve over there. And then I also tested that assumption that we made about the heat of reaction being approximately constant. So remember we said delta Cp often worked out to be a number small enough that we could make the approximation that the heat of reaction is approximately the same as the standard heat of reaction. So that's also simulated there. So you can see similar values in each case, and so we can see the conversion is dropping with temperature like so. Okay, any questions or comments on that? Right, I guess that's not much we can say there. And then also further to testing that assumption here, we have just increased the flow rate through the jacket. So from 5 moles per second to 50 moles per second. And you can see these 2 lines are closer together now. So instead of applying the assumption that the flow rate is very much faster, if we also simulate the case of the flow rate being 10 times faster, you can see that assumption line becomes closer to that simulation line, that log mean temperature difference line. Okay. So I think all the code is in here. Okay, it's actually not here, so I'll post up the code so you can play around with this also. But basically, it's just simulating the same equation. Right? So we are simulating this equation numbered 48 here, and we are just testing the assumption. So we are looking at leaving this delta Cp in and then removing it. And we are looking at a log mean temperature difference here instead of the straight Ta minus T. So, so that's showing us that we can establish a relationship between conversion and temperature. So that's not yet showing us design. So let's look at modifying some of our basic reactor types and doing a design now. So here we have our tubular reactor, and you can see here we've got our jacket. So it's a double pipe sort of arrangement. So in the outer pipe, well, I don't want to call it the shell. It's not like we have multiple tubes, but it is a shell, and you can see the jacket fluid is flowing on the outside of the reaction tube. So the reaction tube has this component A entering here and leaving there, and the temperatures are defined, T in and T. And then the jacket has TA1 and TA2. And of course, if M jacket, this should be M dot jacket, that's the mass flow rate through the jacket. If that's much higher, then TA2 is approximately the same as TA1. So this relationship, of course, was derived independently of the mixing type. So the same equation is true. Remember, the only approximation there was that it was steady state, not approximate. The only assumption was that it was steady state. And then if we say that this is an adiabatic system, so let's say we don't have fluid flowing around in the jacket, then it becomes simply this equation 51. So you can see here the Q term will vanish. And then also, we don't have shaft work. We normally understand for a tubular reactor, we aren't adding a stirrer also into that tube. So we normally ignore that term, leaving us just with these two terms. So that's the equation now. And then we get this relationship, a kind of direct relationship between conversion and reactor temperature. So that's still the energy balance. And then, of course, now we want to couple it to our mass balance. So this is our design equation for the plug flow reactor. And remember that this RA was where the temperature dependence arose. So the term on the left-hand side just tells us how the conversion changes across that reactor, just tells us the number of moles as it varies along the volume of the tube. Whereas the right-hand side tells us what nature is doing. So nature is giving us a particular reaction rate given a particular concentration and a particular temperature. So that's where the temperature dependence will arise. So before, we had been doing isothermal reactor design, meaning the temperature was always constant. Now, of course, we want to replace that temperature with this relationship. So we can say we now have temperature as a function of conversion. So we can substitute for the temperature dependence in this RA, and we'll have an equation just in X now. But of course, now it's a more complex relationship because of this equation that's going to be substituted in here. So extending that same example again, we are given the molar flow rates of A and B, and the volumetric flow rate and the temperature. So that's the feed temperature. It's fed with that temperature. And the components, well, actually, it's slightly different now. We've got the different coefficient here. Well, actually, I think that was the same as the coefficient we used before anyway. So anyway, that's the reaction. And then, okay, this is different because now we've got the reaction rate here. And you can see it's first order just in A. So we are assuming that B doesn't influence the rate expression. So of course, this is then a non-elementary reaction. right? It's the case that that elementary reactions would normally require CaCb squared, but here we don't have that. And of course, this might also be just because B is the concentration of B is high enough that we don't its concentration doesn't reduce due to reaction. So it might simply be that, and we've lumped the influence of that hidden Cb squared into the constant here. So anyway, that's there. And then, of course, we've got our Arrhenius relationship for the constant. So that's our temperature dependence here. And then heat capacities and heats of formation are all given. So that's just given in the vector form. So for each component that's known there. And looks like here we are ignoring that inert that we normally add. So the tube volume is 50 cubic meters, and this is the same as the case where we are ignoring the influence of the shell, so we don't have heating or cooling here. And so we can, if you read this code, it's pretty clear to see how we are solving this. So we've got the heat of formation and the heat capacities there, and then of course these are the constants, so it's A plus 2B, so you've got the 1 and 2 gives us C plus 3D, so you've got the 1 and 3 over there. And then the inlet molar flows, if you look at the question, it's saying that we've got 2 moles and 4 moles. So of course, 20 and 40. So 20 over 20 is 1 and 40 over 20 is 2. And we are not feeding in C and D, so the theta vector looks like that, right? And the rest is there. Okay, so we've defined A and E, and then we can calculate the heat of reaction here. And then here I'm using an easy finite difference kind of approach to work this out. So I'm just avoiding using ODE 45 here. Right? So I'm just taking, I'm running this loop over a range of Z values. So I'm using the index I to run through the Z values. And here I'm working out the current concentration. So if we just take the current molar flow rate divided by volumetric flow rate, that's the molar amount, and then multiplying by 1 minus x gives us the current concentration in the reactor. And then here applying the Arrhenius relationship for K, we're calculating, we calculate K here, and then we've got Ca over here. So this Arrhenius relationship is using this Ti minus 1, and you can see here we also used Xi minus 1. So it's saying from the previous point we have values for X and T. So of course when we start this out, our previous, you can say we are starting at some initial value here. So at the inlet point, we know a temperature and a conversion. So the temperature at the starting point is the inlet temperature. And then of course the conversion there is a 1, is 0, right? X naught is 0. And then we run I from 2 onwards. So when we look up I here, I minus 1 refers to the first element. So it looks up T1 and X1. And so we just read off those and we get the concentration and conversion. And you can see here we can calculate then dx dv, so Ra over Fa naught. And so we can just add that forward in time. So that's just taking the approximation, right? It's a simple first order, well, not first order. It's this simple approximation. So we are just taking dx dv so dx dv is approximately x I plus 1. Sorry, the way we did it is actually xi minus xi minus 1 over vi minus vi minus 1. And so here you'll see Vi minus Vi minus 1 is taken to be constant. So if we take equal volumes and equal spacing in the volumes, then that dV is fixed over there. And so, so we can just calculate the next xi value. So we just solve this equation for xi. So this is a known thing. dx dv is known because here we've calculated dx dv. So that's a known number there. And so we can calculate xi over here. And then ti similarly, well, not really similarly, ti, we are just using this relationship for. So if you look here, see we've got this relationship. So we can just take equation 52 and solve that for t. So it's saying we can just write t in terms of x. So because we are solving for x at each position down the tube, we can just use that x value here and solve for t back from there. So that's what we do. We just rewrite that equation in terms of t and then use this x value that we calculated over here. And then, of course, we should work out what volume we've accumulated to. So we just add up the volume as it increases down the tube. And we can plot those results, and it looks like that. So that gives us conversion as a function of volume, and you can see the temperature is also rising. So again, this is an exothermic reaction. So as the reactants are converted, we on balance gain thermal energy. Okay, any questions or comments there?
Not really with the theory, but you said we have to derive every formula we use in a test or exam situation. Equation 52 for conversion, if I'm correct, if you want to use that in the test, I mean, there's 51 equations before that one.
Yeah, so yeah, when I said you have to derive everything from first principles, and given that the equation number here is 52, does that mean I have to derive that much? No, so normally I'll give you some starting point. So I might give you 52 as the starting point to answer a more interesting question than that, or if it's a question that says derive this thing, then I probably wouldn't ask you to start all the way from scratch, right? I'll probably give you some intermediate stage to start from. But yeah, in fact, it's not that there are 52 actual equations there. A lot of it was because of the explanations in between, right?
No, but for example, if it's a question not to do with derivation,
Yeah.
and it's a question based on using a formula or to figure out a value in a problem that's not directly related to this, then can we just say, well, we know that
Yeah, see, in the questions that I'll put to you, um, I'll allocate credit to the derivation part of it. So in designing the question, I will look at how much work is needed in terms of the derivations and so on. So the time that will be required for that will be factored into the question. So you should have enough time to do it. Okay, hopefully, right? It's designing questions is not a precise thing, but generally speaking, there will be, some questions might have a bit more time, some less. So it should average out over all the questions that we have in whatever it is, test or exam. Right. Okay. So that's that example. And now, of course, we want to generalize that a bit further and consider, well, what if we do have heat transfer happening in here? So let's say we are adding heat along the tube, then we'll, of course, have to integrate this up to each point. So along the tube, right, if that's the reaction tube here, and then if we've got our heat transfer tube out here, then in this case, what we should do is say, well, we can't, if we are interested in the conversion up to some point in the tube, let's say we would like to produce a graph like this, right? we want to know how conversion is going to rise through that reactor. And so we want to know the value of conversion at each of these intermediate stages. Then you see it's not enough to just average the temperature difference across that whole tube, because we might be, the value for the overall tube, for the whole tube, might be different to the value, will generally be different to the value up to these intermediate stages. Right, so what we really want to do is accumulate the heat added to the fluid as it's passing through the tube, right? So in this case, we can say we would rather evaluate the temperature variance across the tube, and if so, we should actually also monitor the temperature variance in the tube itself. Well, there we could actually say if the flow rate through the heating tube, heating or cooling tube, if the flow rate of the heat exchange material is high enough, then the temperature on the tube side could be approximately constant, right? So if it's approximately constant there, still it might be the case that the overall temperature difference will not generally be the same as the temperature difference up to any specific point, right? So the fact that the reaction mixture's temperature is changing along the tube, that also affects the degree to which the temperature will rise, and hence it also affects the degree to which the conversion will change. So that's really the influence of concern to us here, that because the rate of change of conversion is dependent on reaction rate, and because we know reaction rate is a strong function of temperature, then the change of conversion down this tube is strongly dependent on how the temperature is changing through the tube. So although we've made some approximations, we've gone back and checked those, and we found that they were fairly good approximations, and we have to keep doing that. We don't want to rush into making approximations that might give us an incorrect temperature change. So remember we said that there's a rule of thumb that's crept into this field, which is for a 10-degree rise in temperature, the reaction rate can double. So if you can imagine, if you imagine this case where, let's say, we've got two temperature profiles, and let's say we make a 10-degree error in our calculation, then you see the conversion that we might get for this curve might do something like this, whereas the conversion we get in the other graph might do something like that. And you see, in that case, we would get totally the wrong estimate for the volume. So we might get a factor, an order of magnitude difference in the volume that we predict. So if we say we are going to settle for a particular conversion, we might get very different volume predictions, and that can totally change our design costs. And so the accounting for the temperature has to be done carefully, or it might invalidate our design. We might get a result that says it's not a feasible design when actually it is, just because we didn't account for temperature correctly. Right, so when we do this, we are going to now integrate for the net heat added along the volume here. So of course the heat added we can get by integrating through the area that's available. So remember that the heat that's added, it's UA delta T, where A is the area of contact. So the contact area in this case is this interface between the fluid of this jacket and the reaction mixture. So if we are integrating in terms of the volume of that reactor, remember we are writing all of this in terms of dx dv. So if we are writing all this in terms of the volume of the reactor, then the integration variable is that volume. So what we need to do then in accounting for this area is write this area in terms of that volume. So we define that small a that you see in the notes as being the area per volume. So you can say that's VA dV. So for example, in this case, if we have the area for a particular Z change here, so that's a delta Z, and then let's say the radius of this inner tube is RT. So we can say the area in that case is equal to 2 pi r, right? So the circumference, 2 pi r t, I should say, times delta z. So that's the area of this inner tube, the outer area of the inner tube, right? Just 2 pi r t delta z. And so for that particular change in delta z. And then we have to look at also the volume of this space. So we need the outer volume here. Well, we could choose to do it in terms of that volume, but actually, volume of interest is the reaction volume. So it's this volume. So it's also RT here. So that volume is it's pi r squared, pi RT squared times delta Z. So you can say here A over V is equal to 2 over R, 2 over RT. So that's area as it varies with volume down the tube. So when we perform this integration, we can convert A to V by using this area here. And in the notes, it's written in terms of diameter instead of radius. So it's 4 over diameter or 2 over the tube radius. Is that clear? Any questions or comments there? Right, so we've got the area accounted for in our calculation for the total amount of heat added to that system now. And we've got our general relationship. So we've got our general heat balance, and here we are neglecting shaft work. We said we aren't doing shaft work, and it's just that now we are retaining this Q dot, where in the previous example we had ignored it. So we are still saying let's keep that energy balance as it is, and the design equation is here. So the variance of conversion with volume is what we have to integrate. So now we can say, well, let's try and combine these two equations, right? So x appears here without differentiation as we have it here. So what we could do is simply differentiate equation 56 with respect to volume. So if we consider all the factors that are varying with volume, you can see here this Q dot. We've just said the amount of heat that gets accumulated is volume dependent. So as we look down the tube, we get more heat being added to that reaction mixture. So that's a function of volume. Then also, if you look at this equation, T in, of course, doesn't vary with volume. That's just the temperature at which we are entering. However, we integrate up to this temperature in the reactor T. So that temperature does vary with volume. So we have to watch out for that one. And then here, this is the heat of reaction at a specific reference temperature. So that won't vary with volume. But here you can see another T, so that one is varying with volume. And then also this X, of course, is varying with volume. So these 1, 2, 3, 4 things we have to be sure to differentiate in. And so that's what we do down here. So you can see dq dv, and then when we differentiate here, you can see that we take the factor in here, and then we take a dt dv. So we've got dt dv times not times, we are integrating in t here. So then when we differentiate this, we take this factor and then times dt dv, right? So that's just the chain rule of differentiation. Okay. So that will give us this term here. And then you can see there's an additional term written in these brackets, and that's because down here, also when we differentiate this particular term, then we'll take delta Cp times dt dV. So we just group those two together in this equation. And then the rest of it, of course, if we differentiate this part in the temperature differentiation, that's 0. But then we are differentiating all of this with respect to, we are differentiating this x with respect to v as well. So we've got a dx dv here, and then when we differentiate this term on the inside, we get that additional term that we group in here. So maybe I should say that a bit differently. When we differentiate this first term here, we get this first part of the equation, right? Theta Cpi times dt dv. Then when we differentiate this term, there are two functions that vary with volume. So we can say, okay, leave this as a constant and differentiate x with respect to v. So that gives us this whole term down here. So you can see what's in the square brackets here is the same as what's in the square brackets here. And then we say, okay, then leave this constant and differentiate this stuff with respect to v. So when you differentiate this first one with respect to v, that becomes 0. And then when we differentiate this, we get delta Cp times dt dv. So that's this part of it here. So we are multiplying by Fa naught x times delta Cp dt dv. So that's that there. Right, so this lower term here, we have to do a product differentiation, and then there's a chain differentiation in there. So maybe just do it, just write out the whole thing, differentiate the whole thing out, and then just regroup it, and you'll see that you get this equation 58. Any questions or comments there? So the TDV, we can say simply, well, earlier we had established this relationship. So the QDV is clearly UATA minus T, right? So we can substitute that in for dQdV, so that's where we had the dQdV term. And then also we can say, well, the XdV for a plug flow reactor is simply minus RAV. So we replace that down here. Right, so we leave the dTdV as it is, and then in this equation where we have dxdV, we just rewrite that as the minus RA. So we just replace that there. So that's the form of equation that we have now. And then we can rewrite that a bit, well, we just rewrite it in terms of dTdV. So that's the equation we have now. And so you can see here that this equation does depend on temperature and conversion. So behind this reaction rate, this RA over here, there is an X that we have to find. And then also X appears here explicitly. And we know that X is going to vary with volume. So we need to solve this equation simultaneously with this one. And of course, this equation also, it is dependent on T, right? Behind this RA is a strong T dependence, so we do need the state variables here as well. Right, so you see, these two equations do have to be solved simultaneously for us to get the solution. Right, but it's a closed set, and you also have to ask then what about the boundary conditions. And well, this is a first order, well, not first, this is a set of ODEs, and you can say that we do have the initial conditions for these. So for temperature, we know the inlet temperature, so we can claim that. And then for conversion, we can say, well, nothing is converted until we go further down the tube. So x at v equals naught also. So we have the initial conditions for these equations. So of course, the usual thing, we take the same components and reaction as before, and now we are applying this non-adiabatic plug flow reactor, and the same jacket characteristics, we'll use the same characteristics, and the reaction rate is given here. the rate constant, I should say. And so we can just apply those two equations and integrate that, and that's the solution we get. So here we get conversion and temperature varying like this. Okay, so the point is, I mean, although that looks like, okay, well, we just take the equations and use them, and that is the result, there's nothing more we can say. But what's significant is we couldn't before do this, right? Before, in the face of the temperature changing, we had no clue how to get a conversion. We couldn't get conversion as a function of volume. Before, it was all under the assumption of temperature being constant. So now, even though temperature is varying significantly, we can still predict the conversion changes. You can see here also over 1 meter of tube, the conversion doesn't rise much, right? It's slightly more than 20%. So we've got a significant loss in temperature here. So the reaction rate is going down pretty fast, and so the conversion doesn't rise as rapidly as we've seen in the previous examples. So of course, that's all dependent on the choices of constants and so on that we used, but I didn't really change the constants from those previous examples. So in the previous examples, we got conversions on the order of 60 odd percent, and now for similar values, we aren't seeing as high conversions. So you can see that the temperature does play a significant role in this whole business. Any questions or comments there?
If we went back to first do the initial mass balance,
Okay.
and the generation term was integral RAPV, and we would, before we would just say RAV, so for the control volume, because we said that the reaction term was constant with respect to all the places in the reactor.
Right.
So how can we how can we start with first principles now knowing this, because we can't any longer just say RAV?
You
Because
see,
I thought that's how we got that equation 57.
no, this one we didn't say RAV. We said specifically there that RA is definitely changing with V. So as we are, even in the isothermal case, you do have the concentration varying across the tube. So we didn't apply that approximation in that case. It was only for the CSTR that we could say RA is the same at all points. So yeah, maybe I didn't emphasize this, but all these developments are specific to a plug flow reactor. Um, in the previous lecture, we had done the CSTR. So in the previous lecture, remember this relationship that we came up with? Yeah, we sort of didn't finish this one because we didn't say how do we now use this to do our calculations. And well, this example that we did is where we are doing these calculations. But in this previous section, we said that we would use that the rate is constant everywhere in the tube. It's just that we didn't know what the temperature is also the same at all points in that CSTR. It's just that we didn't know for a given temperature what conversion we would achieve. So in this example, we are trying to show that, okay, if we achieve this temperature, then this must be the conversion and so on. And so as we select a different point in here, that basically selects a different volume. So let's say we say, okay, we can settle for this particular conversion. So we use this value and we can get the temperature there, and then we can substitute those values back in our design equation to work out what volume that is. Right? So this part is the CSTR. But for the PFR, we didn't make that approximation. So here, when we write this, we are assuming that RA is a function of X, which is varying with volume. Yeah. And if you look back in the first set of, in the first week of lectures, we didn't make that approximation for the PFR. Okay. Any other questions or comments there? Okay. So we can say that we can now write these balances, the mass and energy balances for the CSTR and PFR, The batch reactor case, you could say, in a way, is analogous to the plug flow reactor case. But I actually don't want to do that. I know we've been saying that up to now, but there are quite a few interesting things you can do in controlling a batch reactor. So we're going to come back to the batch reactor when we look at unsteady state operation. So all of this was under the assumption of steady state. We said we can reach steady state in the energy balance. So a bit later, when we cover unsteady state energy balance, then we'll do the batch reactor again. Right, so for now, I want to say we, at least for the CSTR and PFR, we have the operating lines. In other words, we can get conversion and temperature as a function of reactor volume. And let's now apply that in the case of equilibrium design or equilibrium conversion in the reactor. Although it's probably time for a break, right? So let's take 10 minutes and then we, sorry? If you